Well, hello my dear students and viewers. In the previous lecture, we were discussing inexact line search methods to find step length for a general descent algorithm. Now, in this lecture, with the help of one or two inexact line search methods or with the help of the exact line search method, we will find the global convergence of a general descent algorithm. Needly, in this lecture, we shall describe two global convergence results for descent methods. The first one is related with when we employ the step size with the help of exact line search, and the second result is related with the global convergence of descent methods when we employ inexact line search. In the previous lecture, I have mentioned four different types of inexact line searches. Out of those four inexact line search methods, I will consider the wolf condition, and we will show that a descent method with the step length being chosen with the help of the Wolf-Powell rule converges globally. For other three inexact line search methods, I will give sufficient references from which you will get the global convergence of a general descent method where we employ the inexact line searches of those three types. Before getting into the global convergence of descent methods with exact and inexact line search methods, let us recall quickly the structure of general descent algorithm that we have described one or two lectures before. A general structure of descent algorithm is as follows. We consider a function that has continuous first order partial derivatives, and then in this algorithm, our aim is to identify a solution to this problem. By a solution to this problem, ideally we mean we are endeavoring to identify a point x bar say at which this function f has a global minimum. To find a solution to this problem, we start our process with providing an initial point x naught and a tolerance level epsilon for the equation grad fx is equal to 0. Then we initialize the iteration counter number k to be is equal to 0 and move to the main steps. In the main steps, at first we check whether grad f at xk has norm less than epsilon. If less than epsilon, then we stop the algorithm and provide the point xk as a stationary point of the given objective function, and this stationary point may possibly be a global minimum of the objective function. If, however, norm of gradient of fxk is bigger than or equals to epsilon, then we repeat all these steps 2 to step 5. That we compute at the point xk a descent direction dk, and along the direction dk we take a step length of amount, let's suppose alpha k, and subsequently we update the current iterate xk by xk plus 1, which is given by xk plus alpha k dk. Then we go for updating the iteration counter number k by k plus 1, and then we go to the step 1 again. Check whether norm of gradient of fxk is less than epsilon. If not, then again go on repeating these steps, step 2 to 5, until we reach at a point xk at which norm of the gradient of fxk is less than epsilon. Now here in this lecture, we will prove that if this alpha k is chosen by the exact line search method, then this method converges globally. Afterwards, we shall also prove that if this alpha k is chosen by one of the inexact line search methods that we have described in the previous lecture, this method is also globally convergent. Now here, what do we mean by global convergence? By global convergence, we mean that for any initial point x naught taken arbitrarily from the n-dimensional Euclidean space Rn, this method is going to generate a sequence xk that converges ideally to a global minimum of the objective function. But getting a limit of this sequence xk, a global minimum of the objective function, is really too much to expect. At least when f is not convex. So let me first delineate the type of convergence issues that I would like to clarify in this lecture. I will first discuss informally these issues, and Then I will state and prove the associated convergence results. Given a descent method like this one, which has general structure like this one, here this descent algorithm is also known as gradient descent algorithm because we commonly use the information of gradient to identify a descent direction dk. Now, given a gradient method, ideally we would like to generate a sequence xk that converges to a global minimum. However, unfortunately, as I have mentioned, that this is really too much to expect, at least when the function f is not convex. Because for a non-convex function, there is presence of several local minima that are not global. And gradient method is just like a guided downhill that guides us to reach at a near local minimum. By that I mean, if let's suppose this is the graph of the function f, and if we start our algorithm with a point that has corresponding point in the graph, say at this point, then a descent method guides us to reach at a local minimum. And this gradient method is really oblivious to the global structure of the function f, and thus a descent method can easily get attracted to any type of minimum, global or not. Furthermore, if a gradient method starts or lands at any stationary point, including a local maximum, it stops at that point. Thus, the most we can expect from a gradient method or a descent method is that it converges to a stationary point. Such a point is a global minimum if the function f is convex, but this need not be so for non-convex problems. Thus, it must be recognized that gradient methods can be quite inadequate, particularly if a little is known about the location or other properties of global minima. For such problems, one must either try an often difficult and frustrating process of running a gradient method from multiple starting points, or else resort to a fundamentally different approach. Generally speaking, this depending on the nature of the objective function f, the sequence xk generated by the gradient algorithm need not have a limit point. In fact, this sequence xk is typically unbounded if the function f has no local minima. If, however, we somehow get to know that the level set, the initial level set L naught, given by the set of all points in Rn for which the function values are less than equal to fx naught. If we somehow get to know that this initial level set L naught is bounded, then you notice that this sequence xk generated by the algorithm is a bounded sequence because all the points in xk's are inside this initial level set L naught. Because we are generating the sequence xk such that the decency properties hold, so we have this fxk plus 1 less than equal to fxk, and ultimately this is less than or equal to fx naught, and hence the sequence xk generated by a descent method lies inside this initial level set L naught. And if we somehow get to know that this initial level set L naught is bounded, then the sequence xk is bounded. By Boolean-Weierstrass theorem, then this sequence xk must have at least one limit point. Even if this sequence xk can be guaranteed to have at least one limit point, but this sequence converges to a single limit point may not be so easy to guarantee. However, there is a fascinating result which is known as the capture theorem. I will discuss this capture theorem in detail in one of the next lectures, where we will find that it can be shown that these gradient methods or these descent methods that I have stated here, they are commonly attracted by isolated local minimum point. That means once a gradient method or a descent method gets sufficiently close to an isolated local minimum, it converges to this particular local minimum. In this lecture, we are aiming for showing that a general descent method under certain mild assumptions on the objective function f generates a sequence xk for which we get the sequence of gradient values grad fxk that converges to the null vector as k tends to infinity. This is precisely the meaning of global convergence that we have stated in one or two previous lectures. Before getting into the proof of this global convergence, let me pick out a few sentences regarding the approach of global convergence and the mathematical assumptions that I have to be taking in the statement of the global convergence results. These few sentences that I will speak now are not only applicable for the results that I will describe today, but also applicable generally for any of the results that I will be describing throughout this entire course. Here I will quote a few words from the book by Bartsekas entitled Nonlinear Programming. In the entire course, we will give a number of mathematical propositions related to the convergence of several optimization algorithms that I will describe. The meaning of all these propositions sometimes are quite intuitive, but their statements sometimes will look awkward because to reflect algebraically our quite intuitive idea in terms of mathematical expressions, we will require sometimes several complicated notations and mathematical assumptions. Furthermore, when I will be proving the results, you will find that they will quite often involve tedious the epsilon delta argument in checking continuity or convergence of a sequence. So at the first sight, maybe you may wonder whether you really have to go through all of this. A similar question was faced by Euclid as well. When Euclid has derived several of his results on geometry and it was given to Ptolemy, the king of Alexandria, then Ptolemy also have asked to Euclid a similar question that to understand geometry, does Ptolemy need to defend himself in all the mathematically tedious arguments given by Euclid? Then Euclid replied that there is no royal road to geometry. However, for the subject of optimization, the answer for whether we really have to go through all of these tedious epsilon delta arguments or not, we do not have a simple answer like this. There is no royal road to optimization. Geometry as a subject that may be developed without regard for its practical application. Although several practical applications are there today, but when developed it was mathematically rigorous and without bothering whether practical applications are there or not. But in the eyes of most people, for optimization, the value of an analysis or algorithm in nonlinear programming is judged primarily by its practical impact in solving various types of problems. It is therefore important to give some thought of interface between convergence analysis and its geometrical intuition so that we will be able to cope up our common intuition and its expression in terms of complicated mathematical assumptions or mathematical inequalities. Very interestingly, this optimization as a field arose out by the need of practical application as well as by the need of mathematical development. Being a student of mathematics, we always try to look at any given problem from the general perspective. We being mathematics students, at the first glance, look at the problem from the general perspective. That means we are given any general function f that is just known to have continuous first order partial derivatives. Now given this minimization problem, mathematics students always try to see if they can devise an algorithm that can solve this optimization problem for any given objective function f. But when this problem goes to a practitioner, they will feel for a given expression for f, whether this general algorithm will be able to solve his or her particular problem with particular expression of the function f. This optimization field got developed by joining hands of both mathematicians as well as practitioners. From the perspective of mathematicians, convergence analysis is one of the primary focus in the development of an optimization algorithm, that they would like to develop an optimization algorithm that has a nice convergence behavior. And while developing an optimization algorithm, mathematicians always quantify everything with extreme extent through mathematical statements. And these mathematical statements or assumptions are quite loose and applicable for a general given objective function f. Here, a simple and elegant proof for the convergence analysis for a general objective function is of prime importance. The rationale is that here simple statements and proofs are more readily understood, and general statements apply not only to the problems at hand but also to other problems that are likely to appear in the future. On the negative side, here for mathematical viewpoint, one may remark that simplicity is not always compatible with the relevance. The mathematical assumption that a mathematics student has taken might not fit into the problem at hand, and thus broad applicability of the assumptions is often achieved through assumptions that are hard to verify or appreciate. This criticism is always there, not for mathematical optimization, but this criticism is always there for any abstract result of mathematics. And thus, from the second viewpoint, from the viewpoint of practitioners, they largely reject the role of mathematical analysis. Here the rationale is that the validity and the properties of an algorithm for a given class of problems must be verified through practical experimentation. So if an algorithm looks promising on intuitive ground, then why to bother with convergence analysis, why to bother with several mathematical ways of writing our common intuition, or why to bother about a very special mathematical way of writing the expression for our assumptions and all. Furthermore, there are a number of important practical questions that are hard to address analytically, such as round of error, multiple local minima, and a variety of finite termination and approximation issues. The main criticism of this practitioner's viewpoint for optimization is that mathematical analysis often reveals and explains fundamental flaws of algorithms that experimentation may miss. These flaws often point the way to better algorithms or modified algorithms that are tailored to some type of practical problems at hand. Similarly, analysis may be more effective than experimentation in delineating the type of problems for which particular algorithms are well suited. So, for both the viewpoints, we have pros and cons, and this whole optimization theory is developed by taking care of both mathematical as well as practical viewpoint. In this course, although I will try to balance between this practice and mathematics, but being trained in mathematics, obviously I will be bit inclined towards mathematics than the practice. Now here let me now go for proving the global convergence of a general descent algorithm when the step length alpha k is chosen with the help of exact and one of the inexact line search. Let me first state and prove the global convergence result for exact line search. We recall that in exact line search, we choose the value of alpha k, the step length at the current iterate xk, by the rule that you minimize the function f along the direction dk emanated from the point xk. That is the point xk plus 1 given by xk plus alpha k dk is a global minimum of the function f along the direction dk. That means we focus our attention in the variable space of the function f on the direction dk that is emanated from xk. So we focus on this ray or on this line and then try to identify the function values fxk plus alpha dk for alpha greater than 0 and filter out which particular point xk plus 1 gives the global minimum. So from here we notice that if xk plus 1 bar is a point given by xk plus alpha k bar dk, where alpha k bar is a step length that satisfies the Armijo rule, then the function value at xk plus 1 given by the exact line search is certainly less than equal to the function value at the point xk plus 1 bar, where xk plus 1 bar is given by the Armijo rule. Now I will state and prove the global convergence of a general descent algorithm when we employ the exact line search. The theorem states the following. Let xk be generated by the general descent algorithm. By this general descent algorithm, we mean the descent direction dk is a general descent direction. That you choose any direction dk that is a descent direction and then you go with generating the sequence xk, and for any such xk the following result is true. When we take the step length alpha k chosen by the exact line search, or we also refer it as minimization rule, because we employ a minimization here to find the value of alpha k. So you take this sequence alpha k generated by exact line search. Now we suppose the gradient function grad fx is uniformly continuous on the initial level set L naught given by the set of all points in Rn for which fx is less than equal to fx naught, where x naught is any arbitrarily chosen initial point from the n-dimensional Euclidean space Rn. Also let that the angle theta k between the negative gradient at xk and the chosen descent direction dk for the kth iteration be uniformly bounded away from the angle 90 degree, that is this theta k is such that theta k is less than equal to pi by 2 minus mu for some mu greater than 0. A small number, this mu is a small number that is substantially smaller than pi by 2. Then grad fx k is equal to 0 for some k. That is, you will get a finite value of the iteration number k for which xk is exactly a stationary point, or the sequence of numbers fxk diverges to negative infinity, or the sequence of vectors grad fxk converges to the null vector. Here in this theorem, we also have the assumption that the objective function f is continuously differentiable. In fact, this continuous differentiability of the objective function is a standing assumption when we discuss about any descent algorithm or any gradient descent algorithm. Gradient, this term is also used because in evaluating the direction dk, we use the information of gradient of the function f. So here standing assumption is that the function f is continuously differentiable. By that we mean the function f has continuous first order partial derivatives. Now let us go for proving the result that I have stated over here. Before proving the result, let me tell a few words about the condition that we have taken. Because practitioners always criticize with mathematical assumptions. They may feel that these mathematical assumptions may not fit into their problems. Here you may feel that this grad f is uniformly continuous. This assumption is not a sufficiently loose assumption. Then you please notice that if I consider, let's suppose the objective function is twice continuously differentiable, and if we assume that the Hessian matrix has bounded eigenvalues, that means say if is a C2 function twice continuously differentiable, and the Hessian matrix across the points in this initial level set L0 has bounded eigenvalues. This Hessian matrix, you know, is also denoted by this nabla square of the function f at the point x. Let's suppose this Hessian matrix has bounded eigenvalues. Then by the Rayleigh quotient, we have lambda 1, the minimum most eigenvalue of the Hessian, less than equals to x transpose h f x bar for any given point x bar in L0 times the vector x divided by norm of x square for a non-null vector x less than equals to the maximum most eigenvalue of the Hessians hfx for all the points x in L0. This lambda 1 is the minimum most eigenvalue of all the Hessians hfx's where x is lying in L0 and lambda n is the maximum most eigenvalue. Then we see that the spectral norm of the Hessian matrix at any point x in L0 is less than equal to maximum of absolute value of all the eigenvalues of all the Hessian matrices H, F, X, S. So effectively this norm of the Hessian matrix is less than equal to a constant. Let's suppose lambda. Then we will obtain that difference between the gradient of the function f at x and at y is less than equal to this norm of the Hessian, which is less than lambda times norm of x minus y. And therefore we notice that if we assume that the Hessian matrix has bounded eigenvalues, then the gradient of the function f is Lipschitz continuous and hence uniform continuous. You may feel that this boundedness of the eigenvalues of the Hessian matrix may be a loose condition. If you feel even this condition, these Hessian matrices are having bounded eigenvalues, is not a loose condition, it is not a relaxed condition than that of uniform continuity, you may just consider that this L node initial level set is a closed and bounded set. That means you just consider this L node is a compact set. And we all know the Heine-Cantor theorem that continuity of a function on a compact set implies the uniform continuity. And therefore you just consider that the components of this gradient f, that is the partial derivatives of the function f, all are continuous and this L naught is a compact set, then certainly this grad f is uniformly continuous. So this uniform continuity of grad f is not really a very strict condition which is not satisfied by majority of the functions. Now here I would also like to inform the geometrical meaning of this condition, that this theta k is such that theta k is less than equal to pi by 2 minus mu. At the first glance you may feel this condition theta k less than equal to pi by 2 minus mu is really strange. But this condition geometrically means the following, that the angle between negative gradient at xk and the chosen dk is less than equal to pi by 2 minus mu tells us that you choose the descent direction dk to be employed in the algorithm such that if I have the level curve of the function f at xk is, say, this curve, and in this level curve certainly we have the point xk lying, let's suppose the location of xk is somewhere over here. We all know the gradient of the function f at xk is perpendicular to the level curve lk. That means this gradient vector is perpendicular to the tangent on this level curve at the point xk, and therefore the set of all directions, say pk, that are descent can be identified by those pk's which are satisfying the inner product with gradient fxk is less than 0, and these sets of pk values identifies this region, that this below side of this tangent, the red line. So any descent direction dk is lying in this dotted region. Now you go for taking those dk's for which the angle between the negative of the gradient and dk is not close to this pi by 2 angle. So from this pi by 2 angle, you just consider an angle of amount, let's suppose mu. Now within this below mu angle, you consider your dk to be chosen. So you consider to choose dk any direction lying inside this green shaded region, and with a chosen dk in this green shaded region, you go for employing it in the general descent algorithm. That descent direction dk will certainly satisfy this condition, that theta k is less than equal to pi by 2 minus mu. So effectively this condition says that you don't choose those decays which are almost perpendicular with the negative gradient of the function f at the point xk. And this choice of dk, you notice that is at our hand, that we have several possible points inside this green region, and you just arbitrarily choose any dk, and with that dk in this green shaded region you will realize the global convergence. Let us now go for proving this result. Now here what we are endeavoring to prove, we have to prove that given these two conditions, that grad f is uniformly continuous, theta k is uniformly bounded away from 90 degree, that is this direction dk is not almost perpendicular to the negative of the gradient, then you will have the gradient value of the function f a null vector for some finite index k, or this sequence of real numbers fxk is unbounded below, or grad fxk converges to the null vector. We may fall into this case when the function f is unbounded below. So we just go for assuming that the function f is bounded below. If unbounded, then you may fall into this case. We also assume that this grad fxk is not equal to 0 for any k. If it is equal to 0 for some k, then you have proved the result. So we are assuming these two conditions, that this grad fxk not null for any k, and also we are assuming that fxk is not converging to infinity, or the sequence fxk is bounded below. Given these two assumptions, we will go for proving that this gradient fxk converges to the null vector. If any of these two assumptions is violated, then we are under this case, or in this case, that also proves the result. So we straightly go with assuming that grad fxk is not null, and the sequence of real numbers fxk is bounded below. We will prove that the sequence of vectors gradient fxk converges to 0 as k tends to infinity. Now we see that this sequence xk as generated by a descent algorithm is always lying inside this level set L0, and hence the sequence fxk is a monotonically decreasing sequence and bounded below by the lower bound fx naught. As the sequence of real numbers fxk is bounded below and monotonically decreasing, this is a shorthand for monotonically decreasing. The sequence converges, and once this sequence fxk is convergent, this sequence is a Cauchy sequence, and hence fxk minus fxk plus 1 converges to 0 as k tends to infinity. Now assume if possible that on contrary that grad fxk does not converge to 0. If grad fxk does not converge to the null vector, then obviously there exists some positive epsilon for which norm of fxk less than epsilon does not hold for all k values after certain index, or this is greater than equals to epsilon for all k values lying in an infinite subset of the natural number set. Let's suppose that infinite subset of natural number set is capital K, for which for any index small k, inside that set capital K, we have this norm of gradient of fxk greater than equals to epsilon. You notice that this k has to be an infinite subset of the natural number set, because if k is a finite set of natural numbers for which this norm value is greater than equal to epsilon, then you will certainly have an index number k naught, after which this inequality is violated, and hence you will have then this grad fxk will be converging to a null vector. So this capital K is an infinite subset of the natural number set. Now next we will go for only with those elements of the sequence xk for which k is lying inside this set capital K. We write it neatly that in the following: by any k we mean k belonging to capital K. With any small k belonging to this capital K, we see that we have negative gradient at xk transpose dk divided by norm dk is equal to norm fxk into cosine of the angle between dk and negative of the gradient f at xk, that is your cosine theta k. As theta k is lying in between 0 and pi by 2, inside which range the function cosine is a monotonically decreasing function. So as theta k is assumed to be less than equal to pi by 2 minus mu, then we have this norm gradient of fxk greater than equals to epsilon, and cosine theta k is greater than equals to sine mu. Let us denote it as say epsilon 1. We shall use this inequality later on. Let us name it as the equation number 1 say. Now we notice that for any alpha greater than 0, for which this xk plus alpha dk lying inside the initial level set L naught, we have by the mean value theorem fxk plus alpha times gradient f of xi k transpose dk, where xi k is a vector lying in the line segment joining xk and this point xk plus alpha dk. This right hand side expression further can be written as if xk plus alpha times grad fxk transpose dk plus alpha times grad f xi k minus grad f at xk, its transpose times dk, which by Cauchy-Schwarz inequality is less than equal to f xk plus alpha norm dk times grad fxk transpose dk divided by norm dk plus norm of f at xi k minus grad f at xk. We shall come back to this inequality after a while. Let us name it as say 2. Now we look at this expression. As the function grad f is uniformly continuous on L naught, if we assume that the initial level set L naught is a convex set, then we see that this entire line segment xk to xk plus alpha dk is inside L naught, and thus jk is also inside L naught, and inside L naught the function f is assumed to be uniformly continuous. So as f is uniformly continuous on the convex set L naught, and the points xk together with xk plus alpha dk belonging to L naught. Here we are taking up this xk plus alpha dk belonging to L naught because we are going to employ this alpha to be an exact minimizer, and with that exact minimizer of the function f along the direction dk, as the point exact minimizer is also inside the set L naught, we are taking up here is that xk plus alpha dk is also in L naught, and hence ik is also inside L naught. We then have for the positive epsilon as half of epsilon 1, there exists a delta greater than 0 such that we have the norm of grad f at xk minus grad f at xi k less than epsilon 1 whenever the distance between xk and xi k is less than delta, or we just go for assuming that the distance between xk and xk plus alpha dk is less than delta. Here we shall first show that when this alpha or alpha k is chosen in the algorithm with the exact minimization rule or exact line search, then with that alpha k we have this sequence alpha k norm dk converges to 0. And once we can prove that this sequence alpha k norm dk is tending to 0, we will have certain index number, say k naught, after which we will realize that this norm alpha dk is less than delta. And accordingly, we will realize that this inequality is satisfied, and which in turn, once employed in 2, will give us the global convergence of the algorithm. So let us now go for proving that with the exact line search, alpha k times norm dk is less than delta after certain index number, say k naught. To prove this result, we shall take the help of Armijo rule that we take, say alpha k bar be the sequence of step lengths that satisfies the Armijo rule. Then we see that f of xk plus 1 bar, which is a point given by the Armijo rule, that is xk plus 1 bar is given by xk plus alpha k bar dk. As alpha k bar satisfies Armijo rule, we have this quantity less than equal to fxk plus alpha k bar c1 for some c1 in between 0 and half times grad fxk transpose dk, and as fxk plus 1 is the global minimum of the function f along the direction dk, we have this fxk plus 1 less than equal to this inequality. This inequality we have already shown at the beginning of this lecture earlier. So we then have now alpha k bar times minus c1. We are bringing this portion on the left. So grad fxk transpose dk is less than equal to fxk minus fxk plus 1. As this left hand side is greater than equals to 0 and the right hand side is, by our assumption, tends to 0 as k tends to infinity. So in turn we are now getting then this entire sequence converges to 0 as k tends to infinity, and as this gradient of fxk is greater than equals to, we have here epsilon. Let me put here not epsilon because epsilon I have considered later also. So let me say here epsilon dash for some positive epsilon dash. So as this gradient of fxk has norm greater than equals to epsilon dash, so ultimately here we then have the sequence alpha k bar times norm of dk tends to 0. Therefore, this alpha k bar norm dk less than delta after certain index number k naught for some k naught in the set capital K. Then what we see that from this inequality, that the difference between, let us name this inequality by say 3. From 3 we have the norm of grad f x bar k plus 1, where x bar k plus 1 is a point given by the Armijo rule, minus grad fxk is less than epsilon for all k greater than equals to k naught. So we now go to the inequality 2, and in the inequality now we have in the left hand side you go for employing this alpha as alpha k bar. So if xk plus 1 bar is less than equal to this entire quantity on the right hand side, which will give us if xk plus 1 bar less than equal to fxk plus alpha k bar times norm dk times gradient f xk transpose dk divided by norm dk plus half of epsilon 1, where this half of epsilon 1 is equal to epsilon. Now we see that this quantity in the numerator grad fxk transpose dk, we have shown here that in 1 is greater than equals to epsilon 1 times norm dk. So this 1 gives us then this right hand side less than equal to fxk minus half of this less than delta times epsilon 1. and this is happening for every k greater than equals to k naught, because this quantity is less than delta only when k is greater than equals to k naught. And as here you notice that this left hand side is greater than or equals to the function's value at an exact minimizer xk plus 1. So we obtain here that if xk plus 1 is less than equal to if xk minus half of delta epsilon 1 after the index number k greater than equals to k naught, it ultimately shows that this fxk minus fxk plus 1 is greater than equals to half times delta epsilon 1. But you notice that this half times delta epsilon 1 is a positive quantity, which in turn is contradictory to our initial observation that the sequence k minus fxk plus 1 converges to 0. And therefore our assumption that this grad f does not converge to a null vector was wrong, and hence the result follows. So here goes the proof. Voila. French people says this word voila, that here it is. You can use voila to draw attention to something that you can physically see. That here you have assumed that this does not hold, but at the end of the day you are physically observing that, well, we are arriving to a contradiction. So this completes the proof. Quod erat demonstrandum. This QED is a Latin term which is the abbreviation of Quod erat demonstrandum. Now next I will go for proving the global convergence, that this grad fxk converges to null vector for one of the inexact line search methods. That let me pick up the Wolf condition, and for the inexact line search with the Wolf condition, we will prove that a general descent algorithm, when employs the step length given by the Wolf condition or the Wolf-Powell inexact line search, converges globally. Towards proving this global convergence of a descent algorithm for Wolf-Powell inexact line search, we shall here prove the famous Joutentzigs result, which states the following: that for global convergence of general gradient descent algorithm with Wolf-Powell inexact line search. For these, the Joutentzigs theorem says the following. Joutentzig is a famous optimizer who is popularly known for numerical optimization algorithms. One of his fascinating results is the following, that proves the global convergence of inexact line searches. The result states that consider the general descent algorithm where dk is a descent direction and the step length alpha k satisfies the Wolf conditions or Wolf-Powell conditions, which we recall here that the first condition in the Wolf-Powell rule is the Armijo condition, that the function value at xk plus alpha k dk is less than equal to afxk plus alpha k into some constant c1 in between 0 and half times grad fxk transpose dk. And the curvature condition, which gives us gradient of f at k plus alpha k dk transpose dk is greater than equals to some constant c2 times grad fxk transpose dk, where c2 is a quantity in between c1 and 1. Here c1 is lying in between 0 and half, and c2 is such that it satisfies this inequality. Next, we suppose that the function f, the objective function, is bounded below in the n-dimensional Euclidean space Rn, and the function f is continuously differentiable in the entire n-dimensional Euclidean space. Together with, we assume that grad f is Lipschitz continuous inside the initial level set L0. Then the famous Joubert condition satisfies, which says that the summation k greater than equals to 0 cosine square theta k times norm of grad fxk. This series is a convergent series, which we denote by less than positive infinity, where this angle theta k is the angle in between negative gradient at xk and dk. Let us now prove this result. Now from this result we will show that if theta k is bounded away from 90 degree, then this grad fxk converges to the null vector. Let us first prove this result. To prove this result, we see that from the curvature condition of the Wolff-Powell rule, we have grad fxk plus 1 minus grad fxk transpose dk is greater than equals to c2 minus 1 times grad fxk transpose dk. Now, as the function f is assumed to be Lipschitz continuous in L0 and the sequence xk is inside the L0, we have, by Cauchy-Schwarz inequality, this left hand side of this inequality by Lipschitz continuity of grad of f on L0, we have some Lipschitz constant, say capital L, which gives us grad fxk plus 1 minus grad fxk transpose dk less than equal to norm of the first component in the bracket. So that is capital L times norm of xk plus 1 minus xk multiplied with here norm of dk. As xk plus 1 is xk plus alpha k dk, we have further this less than equal to L times norm dk square into alpha k. And by combining this inequality with this inequality, we get, let us name it as 1 and say 2, we get alpha k bigger than or equals to C2 minus 1 divided by the Lipschitz constant capital L times grad fx k transpose dk divided by norm of dk square of it. Now, if we employ this inequality alpha k greater than equals to this quantity on this first condition of the Wolf-Powell rule, here we have not alpha 1, alpha k. In this Wolf-Powell rule, if we employ this inequality alpha k greater than equals to this quantity at the bottom, then we note that from this condition 1, as this portion is less than 0 because dk is a descent direction, so we get from this inequality 1 that which gives from the Wolf-Powell condition 1, the Armijo rule, that if at xk plus 1 less than equal to f at xk plus c1 times c2 minus 1 divided by L into grad fxk transpose dk divided by norm of dk square. Now, as the angle between negative grad fxk and dk is theta k, so we have here this less than equal to f at xk minus some positive constant, say c, where c is altogether these quantities, that c1 times 1 minus c2 divided by capital L, this c times cosine square theta k times norm of gradient f at xk. Here I guess forgotten to write this factor, this bracketed factor, gradient of fxk transpose dk. So here we will have here not just in the numerator this term but its square. So here we will have then square of norm grad fxk. Now from this inequality we notice that if we consider f xk plus 1 minus f x naught, we can write it as by a telescopic sum that from j is equal to 0 to k f at xj plus 1 minus fxj, which by this inequality gives us less than or equals to minus c times summation j is equal to 1 to k cosine square theta j into norm of grad f at xj. So it gives us this sequence of partial sums summation j is equal to 1 to k of cosine square theta j times norm grad fxj square of it less than or equals to 1 by c times f at x0 minus f at xk plus 1. As here we have assumed the function f is bounded below in Rn, we get here that this is less than a finite and definite quantity, say capital M, and thus these sequence of partial sums of the series summation j is equal to 1 to infinity cosine square theta j times grad fx at xj is bounded, and we all know that for a series of non-negative terms, if we have the sequence of partial sums bounded above, then that series is convergent, and hence this series is a convergent series, and that proves the result. You know, a similar result also holds for all the other three inexact line search methods that I have mentioned in the previous lecture. Here I have proved this result, Joe-Trendzig's result, for the Wolf-Powell rule. You can find this Joe-Trendzig's result for the other three inexact line searches in one or two of the references I will mention later. But here I would like to mention that this condition, that this series is convergent, is known as the Joe-Trendzig's condition, and this condition essentially entails us that if theta k is bounded away from 90 degree, then in that case, as the sequence, this sequence is such a sequence that its summation is convergent. Therefore, by the necessary condition of a series being convergent, we have that Joe-Trendzig's condition implies cosine square theta k times norm of gradient at xk square tending to 0 as k tends to infinity. So if we consider that theta k is uniformly bounded away from pi by 2, then we certainly have this cosine square theta k greater than equals to sine square mu, and hence you have this norm of grad fxk converges to 0. And that is what exactly we mean by the global convergence. So the global convergence of the descent methods with inexact line searches can be realized provided that the search directions, these DKs, are never too close to orthogonality with the gradient. Now I would like to mention one book, a very famous book, a theoretically elegant book in optimization by Sun and One, entitled Optimization Theory and Methods, Nonlinear Programming, came out from the first volume of Optimization and its Applications, a Springer book series, in the year of 2006. In this book, you will find the global convergence of general descent algorithms with the other three inexact line search methods, the Armijo backtracking rule, or the Armijo-Goldstein rule, or the strong Wolf-Powell rule. More importantly, you will find that in this book, the global convergence of general descent algorithms with inexact line search methods with the gradient of the function f, a uniformly continuous function, may not be a Lipschitz function. Here I have proven the result with the assumption that the function f is such that the gradient of the function f is a Lipschitz continuous function. But you will find in this book that with the assumption that gradient f is uniformly continuous, there is global convergence of general descent algorithms with inexact line searches. With this comment, I stop this lecture here. In the next lecture, we will have a rigorous discussion on the question that where do general descent methods converge? We will find that the existing result says that general descent methods converge almost always to a local minimizer. Especially the capture theorem also will be discussed in the next lecture. Thank you. Thank you all for all of your kind attention.